Okay, today we're going to talk about rational and irrational numbers. And this relates to the square roots that we've been talking about recently, because some types of square roots are rational numbers and some types of square roots are irrational numbers. So you've actually already seen examples of both of these. We just haven't used this terminology before. So rational numbers are numbers that can be written as fractions. They are also numbers that are written as terminating or repeating decimals. Terminating means stopping, so that would be a decimal like 1.4, because after the 4, the number is over. Okay. Repeating decimals are numbers that go on forever, and they have some number of digits that keep repeating over and over. So like 2.3 repeating. You may have seen that little bar over the top. So 2.3 repeating means that 3 is going to keep happening over and over. It's never going to stop. It'll be 2.3s, and then the 3s will go forever. The other type, and then of course we know fractions, things like 1/4 or 2/5. Those would be ones written as fractions. And then the third type, so we have one type, two types. The third type are square roots of perfect squares. You have a list of perfect squares in your packet on the very front page. Perfect squares are created when you multiply a number times itself. So for example, the square root of 16 is rational because 16 is created of 4 times 4. The square root of 81 is rational because 81 is created as 9 times 9. So these 3 different types of numbers are all considered rational. They terminate or repeat as decimals, they're written as fractions, or they are square roots of perfect squares. All the other types of numbers are called irrational. So irrational numbers cannot be written as a fraction. They are non-terminating and non-repeating decimals, or they are square roots of non-perfect squares. So you can see I'm using a lot of oops, I didn't really have enough room, but that says non-perfect squares. So instead of perfect, non-perfect. Instead of terminating, non-terminating. Instead of repeating, non-repeating. But let's talk about what all these things mean. So it's kind of hard to explain how things are not written as fractions. So just know that if it's not written as a fraction, it might be irrational. But you do need to check these other things as well. Non-terminating means not stopping. So this is going to be a number that goes on forever. It's not going to stop. But it's also not going to repeat. So pretty much what we're going to see here is we're going to see a bunch of random numbers going on forever. So here's an example. 4.12739 ... You will see that ... at the end, because if I didn't have that ... then I would have a terminating decimal. If it stops after the 9, that's terminating. We want it to be non-terminating, so we have to show that it keeps going. We also want it to be non-repeating. Look, I have random digits, 12739. That's not a pattern. That's not repeating. That's just random. Okay. Then we also have non-perfect squares. So that would be like the square root of 20. Okay. There's not a number times itself that equals 20. Or the square root of 50. There's not a number times itself that equals 50. Okay. And then one more thing I want you to write in this irrational number section is I want you to write the number pi. Pi is one of the most famous irrational numbers. Pi, I'm sure you've heard it before. We approximate it as 3.14, but it actually goes on beyond that, and it does not terminate and it does not repeat. Okay, let's take a look here. We've got a bunch of different numbers, and we're going to decide if they're rational or irrational, and we're going to explain why. And you might want to have your calculator close by because you may want to use your calculator for some of these, especially some of these square root ones. All right, so our first number here is -12. So we're going to decide if -12 is rational or irrational. Well, the first thing I want to look is I want to see, does this have a fraction? Is this written as a fraction? Now, -12 is not written as a fraction. -12 is actually called an integer. It's a negative whole number. But I do know that negative 12 terminates. There's no digits repeating. The decimal point for this number is right here. And there's no repeating digits in this number. So I'm going to call this one rational. Okay. And our reason is because it terminates. Another reason we might want to call this rational is because we can actually technically write it as a fraction. Negative 12 is the same as negative 12 over 1. So we could also say it can be written as a fraction. All right, let's look at the next number. The next number is actually the symbol for pi. So I told you pi is one of the most famous irrational numbers, and that's because it's non-terminating and non-repeating. It is random digits forever. That makes pi irrational. All right, our next number is a decimal, 0.6. So when we're looking at a decimal, we want to ask ourselves, does this terminate or repeat? And I see that this stops. There's no bar to show that it's repeating, and I don't have a dot, dot, dot to say that it's going to keep going. So this is a terminating decimal, which means it's rational. It terminates. This decimal is pronounced 6/10, and actually I can write it as a fraction, 6/10. That's another reason why we can call it rational. All right, next number is 7/8. So this is written as a fraction. If you see a fraction, it's going to be rational. There are a few exceptions to that, which we'll talk about later on. But for right now, when you see a fraction that just has regular numbers, it doesn't have any square roots, it doesn't have any pi symbols or anything, then we're going to consider that rational. Why is it rational? It's written as a fraction. All right, next we have a decimal, 0.123456, dot, dot, dot. Now, we've got to be careful with this. 1, 2, 3, 4, 5, 6. It is following a pattern, but it is not repeating. Repeating would be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, or 1, 2, 1, 2, 1, 2. So this is not repeating. And then I see I have dot, dot, dot at the end. That means it's going to keep on going. So this is an example of an irrational number, because it's non-terminating and non-repeating. All right, next one we have 0.33, and I hope you notice that there's this bar over the threes. So this bar represents repeating. This bar is telling us that these threes are going to continue on. So this is an example of a rational number because it's a repeating decimal. Next one, this is the one we're going to use our calculator for. We have square root of 20. So you may be able to do this without the calculator. You can ask yourself, is there a number times itself that equals 20? But if you're not sure, you can also use your calculator. So what we're going to do is we're going to do our square root buttons, second x squared, type in the number 20, and we're going to see if we get a whole number or not. So when I type in square root of 20, I see, oh, no, that's random digits. 4.472135, that's not repeating, that's not terminating, so this is irrational. Okay, and really the reason is because 20 is not a perfect square. There's not a number times itself that equals 20. 20 is 4 times 5, 2 times 10, 1 times 20, but none of those are a number times itself. All right, next we have negative 1.75. That's a negative decimal. And I look at the end of my decimal to see if it's repeating or terminating, or if it's just random numbers forever. So I see 0.75. There's no dot, 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 so it doesn't go on forever. There's no line, so it's not repeating. So this is an example of a terminating decimal. Terminating decimals are rational. And my reason is it terminates. It stops after the 5. And then our last one is negative square root of 121. So again, if you know what times itself equals 121, that's great. If not, you can always use your calculator. So this is negative square root 121, and I get negative 11. Now that negative 11, that's a negative whole number. It's called an integer. That is actually also could be written as a fraction, negative 11 over 1. It's also a terminating decimal because there's no decimals that go on. So this is rational. So there's a couple reasons why we can say it's rational. First of all, we could say it's rational because 121 is a perfect square. It's 11 times 11. We could also say it's rational because it can be written as a fraction. I wrote it as -11/1. The last reason I don't have room, but we could also say that it's a terminating decimal because it actually equals -11 point. You could put a 0 there, but there's no other digits that are going on beyond there. All right, let's look at some of the questions on the next page. This is on page 10 now. It says, practice identifying rational and irrational numbers with the questions below. Joseph wants to find the side length of a square that has an area of 150 square feet. Should his answer be rational or irrational? Okay, so we have a square. The area of the square is 150 square feet. We want to find out what the side length is. Well, squares are a number times itself. That's how we get our area. So we need to think about whether there's a number times itself that equals 150. If you're not sure, you can always square root and see what happens. So let's square root 150. And I see here on my screen that that is definitely not a number, a whole number, 12.24. And I'm going to put a squiggle because it's about equal to 12.24. So is it rational or irrational? That's going to be irrational because of the answer I got on my calculator. All right, which values from the following list of numbers is not a rational number? Explain. And this means it might be one or it might be more than one. So I do need to check all of the answers here. So I'm going to look through and see which is not rational. So it might be easier to go through and see what is rational and then see what's left over. So I know that anything written as a fraction is rational. And I see I have a fraction right here. So I know that 5/9 is rational. So I know that's not going to be my answer. Okay. I also know that anything that terminates or repeats, decimals that terminate or repeat, are considered rational. And I see right here this repeating bar. So I know that if this decimal is repeating, that it's also going to be rational. Okay. Here I have a decimal. This decimal is what I would call terminating. It doesn't repeat. It doesn't have a bar. And it also doesn't have the ... Terminating decimals are rational. So the two numbers I have left are these roots. So square roots, we know they're rational if they are perfect squares. So we need to ask ourselves, is there a number times itself that equals 25? Is there a number times itself that equals 30? Hopefully you know that 25 is 5 times 5. I can take the square root of 25 and I see that I get 5. So this one's rational because it's equal to 5. Equals 5. Now 30, is there a number times itself that equals 30? 3 times 10, 5 times 6, 2 times 15. None of those sound like a number times itself. We can check by using our calculator. Square rooting 30. Oh my goodness, I'm pushing the wrong button. Sorry guys. Square rooting 30. 5.47722. Okay, nope, that's it. That's the irrational number. Square root 30 is irrational. 30 is not a perfect square. There is not a number times itself that equals 30, and my calculator proved that. Brad converted 5/11ths to a decimal, and his result was a repeating decimal. Does this mean that the value is rational or irrational? Okay, well, there's kind of two ways we could answer this. First of all, the number is a fraction. So 5/11ths, I actually already know that it's rational, but also we know repeating decimals are rational. So this is definitely rational, and we can say two reasons. It was written as a fraction, that makes it rational. Or because it was a repeating decimal, that also means that it was rational. Classify each value as rational or irrational. Now, if you take a look at these, we see they're all really similar to each other. We have the same digits in each of these decimals. This one has nothing at the end of it. This one has ... at the end of it. This one has a repeating bar at the end of it. Okay, take 1 second, pause the video, see if you can tell which of these is rational or irrational based on what we've done in the video so far. Okay, hopefully you chose rational irrational, and rational. Let's talk about why. The first number terminates. It stops after the 7. And we hopefully now know that terminating decimals are rational. The second number has a ... at the end. These numbers are not repeating. 4, 5, 6, 7 is not repeating. It goes on forever, and that is irrational. We would say it's non-terminating and non-repeating. That's our reason for irrational. And then our last one is rational because our 7 repeats. If the number repeats, if the decimal repeats, it is rational. So it's rational because it's a repeating decimal. All right, I'm not going to worry about number 5. So you can cross that out. Let's take a look here at the bottom and see what we think about these. Give an example of each of the following. A rational number between 11 and 12. Okay, well, I know I'm going to be between an 11 and 12, so I know I'm going to have some sort of either a fraction or a decimal because these two whole numbers are right next to each other. So I think I'll go with 11.5. I know this is rational because it is terminating. And I know it's between 11 and 12 because it's 11.5. An irrational value less than 0. Okay, well, if it's less than 0, it's going to be negative. And I know there's a lot of options here, but one thing I know that's irrational is pi. So I'm going to make it negative pi. Another option would have been negative. Put a number under this root that is not a perfect square, like 20. Both of those are examples of irrational numbers that are less than 0. A square root that is rational. Okay, so rational numbers, square roots that are rational are square roots of perfect squares. So I need to put something under my root sign that's a perfect square, a number times itself. So you could pick anything you want. I'm going to do 7. I know that 7 times 7 is 49. So I know 49 is a perfect square. Another example I could do here, I'm going to pick 3. 3 times 3 is 9, so I know 9 is a perfect square. These two roots are going to equal 7 and equal 3, so I know that those are rational. An irrational number greater than 10. Okay, so another thing I know that's irrational is when I have random digits with a ... So I'm going to pick a number bigger than 10, like 15. I'm going to put some random digits behind it. And then I'm going to put a ... That ... is really important. That's what makes it irrational. Without the ... it would be terminating, and then it would be rational. So that's just one example of an irrational number greater than 10.